Okay, slant asymptotes. The slant asymptote only occurs in one specific type of problem. In order for you to have a slant asymptote, the degree of the numerator has to be exactly one higher than the degree of the denominator. Let me give you a couple of examples. If we have f of x equals x to the fourth divided by x squared plus 2. The degree of the numerator here is 4, where the degree of the denominator is 2. Okay, that is not going to qualify for a slant asymptote because the degree of the numerator must be exactly one higher than the degree of the denominator. If we have f of x is x squared plus 1 over x minus 1, well, now you should be able to see the degree of the numerator. Degree of the numerator is 2. The degree of the denominator is 1. The degree of the numerator is now exactly 1 higher than the degree of the denominator. This will qualify for a slant asymptote. And it doesn't matter. It could be x to the 6th on top and x to the 5th on the bottom. As long as the degree of the numerator is exactly 1 higher, you will have a slant. So this one has a slant. That one does not have a slant asymptote. So how do we find these slant asymptotes and what does it look like on a graph? Well, that's what we're going to go through. So we'll use the one that we actually have here. To find the slant asymptote, you have to perform some kind of polynomial division. So we have to do polynomial division, which is why we already learned how to do polynomial long division or polynomial division by synthetic division. Remember, in order to do synthetic division, the denominator needs to be a linear function for us to be able to do that easily. Otherwise, polynomial long division is always going to work. So we're going to show it in both ways for this particular case to show you that it works. Let's start off with the long division. It's the one that takes longer. So again, we're going to do x squared plus 1 divided by x minus 1, which means the x minus 1 goes on the outside. X squared plus 1 goes on the inside, but remember you have to include every possible term. So we've got x squared. I don't have an x term there, so I have to include a placeholder for it. So we'll say 0x and then plus 1. So let's go ahead now and perform the polynomial long division. Again, we're assuming that you already know how to do this. So what do I multiply by the x on the outside here to get the x squared here? Well, that's of course x, so that goes there. Then we distribute x squared minus x. That's the x times the x and the x times the minus 1 on the outside. And then we're going to subtract. If we subtract these, x squared minus x squared is 0. 0x minus the minus x actually gives us a plus x, because minus minus is plus. Bring down the next number, x plus 1. Repeat the process. Now what do I multiply times x to give me x? Well, that of course is 1. So I'll multiply the 1, distributing that times the x minus 1, we get x minus 1. And then we'll subtract. So x minus x is 0. 1 minus minus 1 is 1 plus 1, so that's 2. That's our remainder. We have nothing else to bring down. The good news is here, the remainder in polynomial division, when it comes to finding a slant asymptote, is irrelevant. The slant asymptote is that equation right there. It's what you get from the top. And it will be y equals that. So our slant asymptote is y equals x plus 1. What you will see is that this will be a linear function. This is just going to be a line. And we can graph that on a graph, which again, I'll show that to you in just a second. Now let's go through the process really quickly as synthetic division. Remember, the idea for synthetic division was we take the coefficients 1, 0, and 1. We take what would be the number that you would plug in to the x minus 1 to make it 0, which is 1. We take that and we put it in the box. And then we bring down the first number, multiply these two things together. So 1 times 1 is 1, put it here. Add the 0 and the 1, getting a 1. Multiply the 1 times the 1 in the box times the new 1, you get 1. Add those together, you get 2. What you should notice is that this 2 is our remainder, just like we had over here. These 1s are the coefficients. I'm sorry, the 1 is the constant, excuse me, and then this 1 right here is the coefficient of your x term. So I still get x plus 1. Again, the remainder is irrelevant, so we still get y equals x plus 1. Either way you want to do that, it's fine with me. So when we were to go to graph this as a slant asymptote, we're not going to graph the rest of the function here, but the slant asymptote would simply be the equation y equals x plus 1. Well, the y-intercept is 1. It's got a slope or a rise over run of 1, so we would go up 1 over 1, up 1 over 1 to the right, and then down 1, left 1, down 1, left 1. And what you would have is, again, a dashed line that goes through those points. And that would be your slant asymptote. So let's go ahead and put all of this together and see what this thing looks like on a graph. Let's do... actually, let's come back in another video and do that one.